Now what we'd want to do is we want to formalize a little bit some of these ideas about redundant vectors. Specifically part B of this theorem here. This is going to, it turns out this can be a really useful way to characterize when we have redundant vectors or not. So we're going to actually define a new term here. Let v1, v2, all the way to vk, let these be a set of vectors in n-dimensional space. We say the set of vectors is linearly independent if the only solution to the vector equation c1v1 plus c2v2 all the way to ckvk equals 0 is the trivial solution. Where C1, C2, and all these C's equal 0. Okay? Okay, so make sure you understand what's going on here. If the only solution to this equation is the trivial solution, then that means, according to the previous theorem, we don't have a non-trivial solution, which means we will not have a redundant vector. If this is not true, then this can't be true. Because if this is true, this has to be true, right? Remember, these conditions are equivalent. If one is true, they are all true. If one is false, they are all false. Okay? So that means that if I have only the trivial solution to this, the only solution is making all these coefficients equal to 0, then we say the vectors are linearly independent, and that means there's not going to be any redundant vectors. Okay? They are all, in a sense, independent. I can't take one of the vectors away. I would lose information. Okay? If the vector equation has a non-trivial solution, then we say the vectors are linearly dependent. Okay, these are going to be important terms that we use a lot for the remainder of this class. So you want to make sure you understand them. Okay, vectors are linearly independent means there are no redundant vectors. Every vector in the set is giving important information. We can't take a vector out without reducing the span, without changing the set. Okay? It also means that this equation here, this is a special equation that we will reference a lot. It has only the trivial solution. The only way we could solve this is by setting all these coefficients equal to 0. Okay? On the other hand, if we do have a non-trivial solution, then we say the set of vectors are linearly dependent, and that means the set does have a redundant vector. And so there's a vector that if we take it out, it actually doesn't change the span at all. We would still span the whole space. Okay? Notice that we always have the trivial solution to this equation. Okay? So you can't just see if we have the trivial solution. Obviously, if I set all of these equal to 0, it solves the equation. Okay? So there's always the trivial solution. The question is that the only solution to this equation? If it is the only solution, then the vectors are linearly independent. If we have the trivial solution, but then also a non-trivial solution, then the vectors are linearly dependent.